Alright, in this video we're going to review a finite element analysis problem involving beam elements. Alright, let's go ahead and get started. So here's the problem that we have. We have two beam elements lying horizontally with a point load in the middle at node 2 and a moment also applied at node 2. So we have a force of 1,000 pounds and a moment of 50 kip inches being applied. Here we have some properties for the first element: an elastic modulus of 30 mpsi, an area moment of inertia of 21.3 inches to the fourth, a length of 100 inches. Here we go for element 2, an elastic modulus of 10 mpsi, area moment of inertia, same as number 1, and a length of 200 inches. So we're going to use those as our inputs, and we want to find all the good stuff. We want to find our displacements, want to find our reaction forces and moments, and we would like to find our elemental loads in the form of shear and moment diagrams, but we'll get to that later. Let's talk about the solution process. All right. So the same solution steps are involved with this beam problem as we have in the truss elements. And so first we go through and figure out what our elemental stiffness matrices look like. And with beam elements, we just have horizontal elements in this problem, so there's no elemental transformation due to element angle like we've had in some of the truss element examples. And we only consider the transverse direction for displacement, so that's vertical in this problem, and we only consider rotation. So we're not considering the axial, or pardon me, the horizontal displacement, so just transverse vertical displacement and rotation. And then once we're done with the elemental stiffness matrices, we use those to assemble the global stiffness matrix. We go ahead and reduce the global stiffness matrix by applying constraints. Then we apply our loads to that reduced stiffness matrix problem to solve for our displacements. Once we have our displacements, we can throw those back in the global stiffness matrix to solve for our reaction forces and moments. And we can also use those displacements to solve for our elemental results in the form of shear and moment diagrams. All right, so that's our general solution process. We'll get started with the elemental stiffness matrices, and this is just a reminder for a beam element. This is the general stiffness matrix equation. So maybe we can go ahead and forward through this. There we go, there's our, whoops, that's what we wanted to use. So yeah, we have our transverse forces and displacements, and then we have our moments and rotations. Okay, let's go ahead and take a look at what this matrix looks like. There's our force and moment vector. Here is our elemental stiffness matrix. And here is our displacement vector for the element. So all of our beam elements will have this type of formulation. All right, still going with elemental stiffness matrices, but this time looking in particular at element 1. We're going to go ahead and use that same elemental stiffness matrix equation that we had on the previous slide here. And we're just going to go ahead and first substitute those i's and j's for 1's and 2's, because those are the nodes that we have on either side of element 1. We go ahead and substitute the elastic modulus for the elastic modulus we have at element 1. Same thing for our area moment of inertia. And once again, we do the same thing for our lengths. All right, and just for notation, there's our force vector for element 1, that's our stiffness matrix for element 1, and that's our displacement vector for element 1. All right, go ahead and do the same thing for element 2. There's our general stiffness matrix equation for a beam element. We'll go ahead and make the substitution for our nodes to have nodes 2 and 3 in that matrix equation. Then we'll go ahead and substitute the elastic modulus, substitute the area moment of inertia, substitute the length, and that is our general stiffness matrix equation for element 2. And this is, once again, that's just our force vector for element 2, stiffness matrix for element 2, displacement vector for element 2. All right, and for those of you that really like numbers, here is those same stiffness matrices with all the numbers filled out. All right, so it starts off with what we had before, and go ahead and plugging in these values for element 1. We end up with those numbers. Plugging in these values for element 2, we end up with those numbers. So these represent our elemental stiffness matrices for elements 1 and 2 with all the values, representative values, plugged in. All right, here's our full FEA beam problem. And we're moving on to the next step, which is assembling the global stiffness matrix equation. All right, here we have stuff for node 1, node 2, node 3. We consider 2 degrees of freedom at each node. We consider vertical or transverse displacement, and we consider rotation. So since we consider both of those, and we have 3 nodes, we have 6 degrees of freedom total that we'll be considering in this global stiffness matrix equation. All right, first thing we do is plug in all the values for element 1. Well, I'd used lines on this page. We'll get to the actual values on the next page. And we plug in all the values for element 2. And there's some overlap there here in the center where we just add the values for element 1 and element 2 that happen to align in the same cells of that global stiffness matrix equation. All right, and then once again, for people that like values, here are the values for our global stiffness matrix equation. All right, so there's everything that we have for element 1 filled in. We used the same colors we had originally for element 1 just to differentiate it from all these values that correspond to element 2. And of course, we can go ahead and add those up in the middle there to complete our full global stiffness matrix equation. And all those blank cells that we have there, okay, so this is just highlighting what our force vector is, our global stiffness matrix, and our displacement vector. And these values here that are left blank, well, we would just use those as zeros. There would just be nothing there. All right, we're done with the global stiffness matrix equation, so we can go ahead and move on to applying our constraints and creating our reduced stiffness matrix equation, starting off with our global stiffness matrix equation, throwing up our problem here so that we can move forward and figure out what our constraints are. Which degrees of freedom should we constrain? Well, we look at node 1 and we know that the displacement, the vertical displacement in node 1 must be constrained. So we go ahead and cross out that column and cross out the corresponding row. Next, we recognize that due to the fixed constraint here, no rotation is allowed at node 1. So we go ahead and cross out that column and that row. Finally, we look at node 3 and we see that the displacement at node 3 must be constrained, so we cross out that column and that row. And so, if we go ahead and remove those, we end up getting the following reduced stiffness matrix equation. It's almost there. There we go. So, there's our reduced force vector. This is our reduced stiffness matrix, and this is our reduced displacement vector. Moving right along, we're already at applying our nodal loads to solve for our displacements. So first, we'll go ahead and draw our diagram again for this beam FEA problem. We'll go ahead and write out our reduced stiffness matrix equation. There we go. And we'll go ahead and write out what our loads are. So what we have at node 2 in the vertical direction is negative 1,000 pounds. So we'll go ahead and make that substitution there. And for a moment at node 2, we have negative 50 kip inches, writing that as negative 50,000 pound inches, just so we can have consistent units. And of course, there is no moment applied at 3, so we'll just go ahead and substitute M3 for 0. All right, so with that, we can move on to the next part, which is inverting our stiffness matrix. So this is our original reduced stiffness matrix equation. And we can go ahead and invert the reduced stiffness matrix to figure out what our displacements are. And so we go ahead and do that. There is our displacement, our reduced displacement vector, equal to our reduced stiffness matrix. And so this just happens to be the values that you would get if you inverted your reduced stiffness matrix. And here is our reduced force vector. Let's go ahead and make some substitutions for the values. And we go ahead and do that. We can solve for our displacement at node 2, and our rotation at node 2, and our rotation at node 3. And while these are the values, and that is part of our answer, it helps to draw this out to get an idea of well, what does the deformed shape look like? So go ahead and draw in our original diagram again. We recognize that as we start drawing the shape there, we can see that we have a downward displacement at node 2, which corresponds to what we have here, negative 0.537 inches. We have a negative rotation at node 2, and sure enough, we have a downward slope at node 2. And then we have a positive slope at node 3, which is indeed what we have here. And this sort of corresponds with what our intuition would be for this type of loading on this type of problem. All right. So now we're going to go ahead and solve for our reaction forces. We're going back to the global stiffness matrix equation. And so writing this whole thing out, there it is. There's our global stiffness matrix equation. We're going to go ahead and substitute in values. First thing we did is substituted all the constrained degrees of freedom, or replaced all those with 0. And then we replaced what was previously unknown with the now known displacements. And once we did that, we end up getting the following values. Notice that some of these values are our applied loads, and the other ones turn out to be our reactions. All right, let's go ahead and draw this out to see what this represents. So once again, we have our global stiffness vector. That's what we solved for in the previous slide. And it's equal to our applied loads combined with our reaction forces and moments. So we'll go ahead and write out our original values that we got there. And if we split it up, we saw that we got our applied loads, which makes sense. And we got some new values, which are our reaction forces and moments. And so if we were to go ahead and draw out our diagram here, we would see that this value here corresponds to 1,000 pound forces going down. Well, that makes sense. Notice that we have a clockwise moment here, 50 kip inches, corresponds to that negative 50,000 pound inches there. And now we'll go ahead and move on to our reaction forces and moments. So first we have the 820 pounds going upwards at node 1. Then we have the counterclockwise 95.9 kip inches. And then we have 180 pound forces upwards at node 3. And actually we don't have any moment in node 3 because, well, it's a pin joint, so it can't hold a moment. All right, now we're on to the elemental results. So we use those displacement results and we go back to the elemental equations to figure out what the elemental forces and moments are. So this is our elemental stiffness matrix equation all the way back to the beginning of this solving this problem. All right, and so here is our full elemental stiffness matrix equation for element 1. We can go ahead and start tying together each of the pieces of that elemental stiffness matrix equation, and we can go through and adjust it for all the values that we have. There's all the values, and there we go. Okay, these are our displacements, plugging in our displacements, and if we go ahead and multiply that all through, we end up getting 820 pounds for Y1, 95.9 kip inches for our moment at node 1, and negative 820 at our node 2, or pardon me, our vertical force at node 2, and then we have negative 14 kip inches. Let's go ahead and draw this out on our element. There is our element. There we go. There's the 820 pounds at node 1, negative 820 pounds at node 2, 95.9 kip inches at node 1 for the moment, and then clockwise 14.0 kip inches at node 2. We're going to go through that exact same process with element 2. Here's element 2, the equation for element 2's stiffness matrix equation, which involves the forces and the stiffness matrix and our displacement vector. And so we make some substitutions. There's our substitutions for the values of element 2. We can go ahead and go through one more time for the actual numerical values. And we'll go ahead and make some substitutions here. There's a lot of substitutions. There we go. These are our displacements and rotations that occur on element 2 that we found all the way back in step 4. And we multiply those through, we get some values for the forces and moments being applied at element 2. We can go ahead and draw this out to what's happening on our element. There we go, there's the 180 pounds going downwards at node 2, 180 pounds going upwards at node 3. We have the 36 kip inches going clockwise at node 2, and there isn't a moment at node 3, which makes sense because it's a pin joint. Alright, so one last part, which is how do we transform those results that we got into shear and moment diagrams? Alright, so what we do is we look at the nodal directions, and those are the values that we got directly from the elemental stiffness matrix equations. Alright, so these are just what's considered positive for the nodal direction. There's, of course, going upwards would be positive for our transverse forces, and going counterclockwise would be positive for our moments. Okay, so we're just going to go ahead and write those values in the vector. So this vector here is the same thing that we solved for in the previous slides for element 1 and element 2, and that just corresponds to these values that we have written here. Okay, but let's go ahead and consider what is positive shear. Well, positive shear would be upwards on one end, but due to equilibrium, it would have to be going downwards at the other end. So the shear experienced in this beam would be equal to this value V, with one side going up and the other side going down. That would be positive shear experienced in a beam. And so we could write that like this. If we look at the left side, this going up is the same direction as this nodal force, which is also going up. So we could say that that value at node I, or on the left end, is the same as the shear going through a beam. And likewise, since this value on the right end is going downwards, while the positive nodal direction on the right end is going upwards, since that is an opposite direction, we would say the value here is equal to the opposite or the negative of the shear in the beam. Okay, we do something similar for the bending moment. For the bending moment, we consider positive bending to look like this, going clockwise on the left-hand side, counterclockwise on the right-hand side. If you were to bend this bar, it would make a nice smiley face there. So that's considered to be a positive bending moment in the beam. And sure enough, if we compare this moment with the positive nodal direction for a moment, we see that it is an opposite direction. So we would say whatever value that we have here for the left-hand side of the moment, it would be opposite of the bending moment experienced at that end. And the same thing over here on the right-hand side. Since it's opposite, we would have, or pardon me, since it's the same direction, we would just leave it as the same. Now note, even though it says M here and M here, these values aren't necessarily the same. In fact, we saw that they are not the same in the previous slide. So this is just for nomenclature. All right. So now we go towards solving for the elemental results in the shear diagram. We're going to use, here it is, here's our shear diagram, here's some axes, there's the letter V, here's element 1, here's element 2, here's some nodes, nodes 1, 2, and 3, here's element 1, and we have all our values for element 1, and we notice that with element 1 here, Y1, it's the same direction, so we go ahead and put that at 820 pounds on our shear diagram. Alright, here we notice that it's negative 820 pounds, but because it's the second node, it's the opposite direction, so we draw it at 820 pounds. And for beam elements, we should actually always have a constant shear throughout the element. In fact, it's impossible to have otherwise, because we can only apply loads at the nodes. So we have to have a constant shear, and indeed, we do have constant shear all the way throughout element 1. All right, we'll do something similar for element 2. All right, there are the values of our forces and moments that we got from our element 2 stiffness matrix equation. We see that Y2, value of negative 180 pounds, it is the same direction as what is considered positive shear on the left-hand side. So we go ahead and write that with the exact same sign on our shear diagram. And we do the opposite for our shear at node 3. And so where it says 180 pounds, we actually write minus 180 pounds. And once again, we have a constant shear throughout element 2 of negative 180 pounds. All right, so now we go ahead and do the same thing with our moment diagram. Here's our moment diagram. We got element 1, element 2. We have some nodes, and there it is. There's our moment. We'll go ahead and write out our values for element 1 and our values for element 2. These are the same matrices that we had on the previous slide, just now we're going to highlight the moments instead of the shear values. And so here we just write what we have for a moment at node 1 in element 1. This value of 95.9, it's actually the opposite direction of what is considered to be a positive bending moment through the element at that end, on the left end. And so we flip the sign, which is why we have negative 95.9 pound inches, probably should be kip inches there. And we'll go ahead and maybe we'll just go ahead and write that in right now on the fly. Times 10 to the third. Great. All right. And then this is going to be minus 14 kip inches, but that's in the same direction. So we'll go ahead and write that in. And we'll also go ahead and write times 10 to the third. Great. Fill that in. That's our moment diagram for element 1. We'll do something similar for element 2. There it is, negative 36 kip inches, but it's the opposite direction, so we go ahead and flip it. And once again, we'll go ahead and say that's times 10 to the third. And since that's in the same direction, we'll go ahead and write that. Doesn't really matter, 0 is 0, so let's go ahead and finish it off with a triangle. And so this is what any moment diagram for a beam element should have constant slope. So the shear is constant and the moment has constant slope for beam elements. Okay, very good. That brings us to the reflection questions. And the first reflection question we have is, how does a beam element differ from a truss element? So this might actually be related more towards when we started reviewing those videos on the beam stiffness matrix equation, but it's pertinent here. So what are the differences? What difference in degrees of freedom do we have? All right, next question is, how is solving a beam finite element problem similar to solving a truss finite element problem? Okay, what steps are similar? And then finally, and probably the most tricky when we start moving from truss elements to beam elements, is how do we figure out the shear and moment diagrams from the values generated in the elemental stiffness matrix equation? Okay, so those are our reflection questions for this video on how to solve a beam problem using finite element analysis. All right, thank you very much.